Hello, everyone. Thank you for joining my presentation. My name is Carly Thalman, and I am a third-year PhD student representing Arizona State University and the Neuromuscular Controls and Human Robotics Lab. And today I will be presenting our paper towards a soft robotic ankle-foot orthosis, SR-AFO Exosuit for human locomotion, preliminary results in late stance plantarflexion assistance. The ankle joint is responsible for 45% of the power behind human locomotion, and plantarflexion is a critical motion throughout the entire gait cycle. Body propulsion during forward gait requires ankle plantarflexion, which produces propulsion by using muscles in the ankle to push the foot downward and away from the body, which then pushes off the ground in the stance phase. Proper plantarflexion ensures stable weight transfer that allows us to take another step forward. Individuals suffering from gait abnormalities due to stroke or other neuromuscular impairments can experience difficulties with push-off during walking, resulting in increased risk for trips, falls, and a severely decreased walking pace. Passive orthotic devices may not be beneficial to every patient. Rigid AFOs can create a fixed ankle angle that can then cause further gait abnormalities during rehabilitation or walking. The field of wearable robotics has proposed many dynamic and advanced solutions tailored towards providing assistance to a wide range of users, many of which have been widely successful. However, adding additional weight to the foot can cause complications for impaired users during rehabilitation, especially those suffering from hemiparesis or other weakness in their legs. Soft robotics specifically related to post-stroke therapy and rehabilitation strategies for the lower body have been showing promising results in recent years. This is widely attributed to the lightweight materials and reduced issues with joint alignment due to increased robot compliance with the user. My initial investigation into using soft robotics for ankle rehabilitation was made and presented initially at ECRA in 2019. This design focused mainly on assisting dorsiflexion and relied on a portable pump which was worn in a control belt by the user. The main focus of this work was to design, optimize, and characterize a fabric-based actuator that could be worn similar to clothing or a garment when inactive, but still provide sufficient assistance to the user when activated. This was completed successfully with the development of a pneumatic contracting actuator made from heat-sealed fabrics, which was simulated using FEA modeling and evaluated with preliminary participant testing. This paper aims to expand and build upon that previous work with the introduction of the finalized SR-AFO Exosuit, or Soft Robotic Ankle-Foot Orthosis Exosuit. This paper presents new developments to the SR-AFO, including the addition of new actuator placement to assist plantarflexion, a more robust sensor placement overall, and a smaller, more redefined design of the control strategy and hardware. The lightweight materials prevent unwanted alterations to the user's kinematics during walking and from becoming cumbersome or being strewn by having restricted motion or added weight. The sock-like design of the AFO is made entirely from fabrics and is designed to be worn over the user's shoe. It's a one-size-fits-all design, unlike the previous iteration. The low profile of the fabric-based design makes the wearable robot less cumbersome and creates an ease of application in different rehabilitative settings. The contracting actuators run along the back of the user's leg and pull the heel upward when active to produce a positive ankle angle change. Force-sensitive resistors are used to detect gait events and are embedded into the shoes at the heel and at the toe. The controls and hardware for the SR-AFO Exosuit are not carried or worn by the user in this iteration. A tether connects the SR-AFO Exosuit to a control box, which contains all of the electropneumatic hardware to prevent the user from having to bear this weight during rehabilitation. The control box is connected to an external pressure source to provide compressed fluidic actuation to the solenoid valves. The SR-AFO Exosuit is designed to assist ankle plantarflexion, utilizing the intrinsic compliance of the fabric-based design paired with pneumatic actuators anchored at specific points in the body to generate assistive motions without majorly impacting the user's comfort or range of motion. A complete list of all of these considerations for our design, requirements, and characteristics is outlined in Table 1. The lightweight materials and design of the SR-AFO make it easy for the user to don and off. It is donned from the back of the leg, slipping over the heel into an opening in the back of the exosuit. Velcro straps secure the SR-AFO on the top of the foot, around the ankle, and below the knee. The doffing process is quick and easy, only requiring the user to undo the Velcro straps and remove the SR-AFO from the back. The actuators inflate from 40 to 60% of the gait cycle. It's during this point where the GA and the SOL muscles are activated to produce plantarflexion. A pressure threshold of 100 kPa is chosen to reduce the risk of mechanical failure due to cyclical nature of the operation. The natural walking pace of a healthy participant is typically around 1 meter per second, and so the SR-AFO should be able to operate within this range. The contraction percentage of the actuator was optimized via FEA modeling, using the following conditions in equations 1 and 2. The geometries were varied for initial length of each chamber, the distance between each chamber created by the heat seal, and the total number of chambers in completion for the actuator. This work is covered more extensively in my previous ICRA paper. 2 configurations will be evaluated, a single actuator and 2 parallel actuators. The fabrication for these soft contracting actuators uses a TPU-coated nylon, which is thermally bonded with a heat impulse sealer, which applies a uniform heat and pressure to the seam to create an airtight seal. The experimental setup for the quasi-static isometric tests for varying angles of the 2 actuators use a vice clamp, load cell, and a custom housing structure. The vice clamp is fixed to the bottom of the housing unit, and the load cell is supported at the top at a fixed height. The comparison of a single actuator and a parallel actuator is observed at a fixed 0% contraction to track the maximum force output at 0 kPa up to 100 kPa in increments of 10. A single actuator results in a maximum payload capacity of 9.3 kilograms, whereas 2 actuators in parallel in the same orientation and test consideration result in a 45.3% increase to 13.51 kilogram payload capacity. It should be noted that these actuators were tested using a fabric interface between the load cell and the actuator itself. It is thought that using a fabric interface between the two would create a more realistic output on how the actuator would behave when not fully clamped in a vise. The SR-AFO Exosuit used sufficient cycle time to inflate and deflate with a short window. Pressure is held constant at the source, and a solenoid valve is opened to create inflation. The change in pressure over time is evaluated for inflation and deflation for both a single and double actuators under no load conditions. Inflation and deflation are slow under no load conditions, though there is little difference between the rise time when adding an additional actuator. A universal test machine is used to measure the dynamic tensile force response of the actuators to an instantaneous pressure pulse. Various actuator times are predefined by changing the duty cycle applied to the solenoid valve. For each instance the actuator pressurizes, we observe for 0.1, 0.2, 0.3, and 0.4 seconds of the valve remaining open for a complete period of 1 second. Under 0% contraction and loaded conditions, the actuators are able to reliably reach a peak pressure and corresponding force output of 118 newtons at an interval of 0.3 seconds with the lowest margin of error. The SR-AFO Exosuit uses a custom control box which houses all of the electro-pneumatic components required to provide dynamic and adaptive control. A custom voltage regulator board is used to step the voltage down to a safe range to power both the logic board and the pressure sensors, either using a wall source or a battery. A portable air compressor is used to provide pneumatic actuation as a source and is controlled through the use of 3-way 2-channeled solenoid valves. The housing of the control box is made from a custom 3D printed PLA design. LEDs are used as indicators once the box is closed to provide information to the user about the current state of the system. A power switch is provided on the outside of the box to safely shut the system down when no longer in use. For plantarflexion assistance, a simple bang-bang controller is implemented, which continuously reads the analog signals from the force-sensitive resistors, and the timing of the controlled perturbations for the soft actuators is critical based on these sensors. It's critical for ensuring that the user is receiving assistance at the proper interval of their gait cycle. The FSR sensors are embedded into the user's shoe at the anterior and posterior ends of the shoe insoles to provide kinematic data and information that's critical to time events to detect heel strike and weight shift preceding pre-swing. A total of 3 healthy participants are recruited for this preliminary study. Surface EMG sensors were used to monitor muscle activity throughout the duration of the trials after the maximum voluntary contractions and muscle baselines were recorded. Ankle angle in the sagittal plane for dorsiflexion plantarflexion is tracked using a wireless dual-axis goniometer. The participant dons a soft shoe retrofitted with FSR sensors and is asked to walk at a comfortable, preferred speed on a split belt treadmill. Applied force on the FSR sensors is recorded when the participant is standing still to calibrate the sensors for the user's weight. A threshold is then set at 10% above this calibrated value for the FSR sensor in the shoe, specifically in the toe. This is used to detect weight shift and the transition out of mid-stance during walking. Each trial runs for 1 minute at the user's preferred walking speed and is repeated for 3 trials. EMG reduction is calculated by taking the area under the curve between the average of the trials with and without the AFO exosuit. This was done for 40 to 60% of gait cycle for each step. The average GA reduction observed was seen at 13.4% across the 3 subjects, and the average reduction for the soleus was measured at 16.6% during that window. The reduction observed between the window of 40 to 60% of the gait cycle indicates that the SR-AFO exosuit may be able to provide assistance to users during late stance by taking effort away from the primary muscles used in propelling the foot forward at that critical stage in the gait cycle. However, we did notice a significant increase in the TA muscle. However, this is not entirely surprising, as it is the antagonistic muscle to the muscle groups that we intended to assist. We hypothesized that this increase is due to a deflation time that is not quite fast enough to facilitate the walking speeds of healthy participants. We are looking currently at increasing this ability of the exosuit to incorporate a faster deflation time. With no exosuit, the average DP range of motion was observed at 31.27 degrees, while passive exosuit trials showed an ankle DP range of motion of 29.83 degrees. This falls within 0.57% difference from the DP angle of normal gait, which is 30 degrees. When the exosuit was providing active assistance to the user, the average range of motion in ankle DP was observed at 30.54 degrees, which falls within 2.3% difference of the original range of motion with no exosuit on our participants. We also observed an increase in the maximum dorsiflexion angle when the exosuit was passive, as well as a decreased maximum plantarflexion. While these values were negligible, we hypothesized that these are caused by the perturbation of the actuators, which encourages the user to propel themselves forward faster. This leaves less time for their foot to fully push off as far as they need to, and they may not feel the need to push their foot as far down if they're receiving assistance. New and continued work is still being done on the design of the SR-AFO exosuit to improve the overall quality and functionality of the design. Currently, we're working on increasing the capabilities of the contracting actuator to provide better assistance and stronger perturbations that are more reliable. We have also implemented a new actuator for ankle buckling. This design was presented last month in the WearCon 2020 virtual conference. We are also increasing the overall durability of the exosuit by providing a stronger anchor point for the actuators to ensure that there's no slippage between the actuators and the person. There are a lot of new possibilities that we're looking for with the new design and capabilities of the SR-AFO exosuit. With that, that concludes my presentation. Thank you so much to everybody who is here and watching me present this work. I have included all of our contact information for myself and my team. If you're interested to learn more about the SR-AFO, you can check out some of the links to social media and research pages that I have shared on this slide. You're also welcome to reach out to our lab director, Dr. Hyunglae Lee, and see what research is going on in our lab. I appreciate your time. Thank you so much. And I hope you have a wonderful rest of your conference. I can't wait to see the rest of your presentations as well. Thank you.